Welcome you all to this video on fluid mechanics and machinery. Okay, so in this video we are going to see some details regarding the course outcome 4. Okay, so already we have discussed about reciprocating pump and centrifugal pump, so we'll be continuing with the course outcome 4. So this is pumps actually we were discussing. So this already we have discussed about the theory of the dynamic machine. So what is meant by a pump? Okay, so today actually we'll be seeing about the characteristics curves of centrifugal pump. So now actually what is meant by the characteristic curve of centrifugal pump? You can know this is actually defined as those curves which are plotted from the results of various tests. So this actually various tests will be conducted in the laboratory and the results will be plotted, okay, to study the performance of the pump. We are doing certain experiments in the laboratory and what results we have got we will be plotting in the as a characteristics curve. So that is we call it as a characteristics curves of centrifugal pump. So these curves are used to predict the behavior and performance of a pump when the pump is working under different flow rate, head and speed. So when you are varying the flow head, or when you are varying the flow rate, or when you are varying the speed, how the pump is working. So we are predicting the behavior. So the following or the important characteristic curves for the pump. Okay, so main characteristic pump we have for the studying of the pumps. We have the main characteristics curves, operating characteristics curves, and also the constant efficiency. So we'll be discussing them. So first one is actually the main characteristics curves. So what is actually the main characteristics curves is the main characteristic curve of a centrifugal pump consists of variation of head, power and discharge with respect to the speed. So how your head, your power and discharge is varying with respect to the speed. For plotting curves of manometric head various speeds versus speed, discharge you are keeping first one. For plotting curves of manometric head various speed, what happens, you are keeping the discharge as constant. When you are plotting the curve of discharge versus speed, the manometric head is kept constant. Okay, and when you are plotting the curves of power versus speed, the manometric head and discharge you are going to keep it as constant. Okay, so that is the main characteristics curves. Please see the diagram. You can see that the first diagram actually here we have speed on the x-axis and also we do have power, head and discharges along the y-axis, and we have this. You can see that this power, how it is varying with speed, and the discharge and head is constant. Okay, and that is the P power will be directly proportional to the cube of speed cube. That is, in the sense it will be directly proportional. And the second one is actually second curve is H is directly proportional to n square. So the head increases as n square and the Q will be constant. Third one is actually Q is directly proportional to n. So what happens here, discharge is directly proportional to the speed. So here you can see that you get it as a linear curve. Okay, so they are directly proportional and the rate is also the same. So this is actually one of the curves. Next is actually the operating characteristics curves. So see, actually if we keep the speed as constant, so on the variation of manometric head, power and efficiency with respect to discharge will give you the operating characteristics of the pump. Okay, you are keeping the speed as a constant one and how the manometric head, power and efficiency are varying with respect to the discharge will give the operating characteristics of this pump. So the input curve for pumps shall not pass through the origin. Okay, it will be slightly away from the origin from the y-axis. As even at zero discharge, what happens? Some power is needed to overcome the mechanical losses. So when you are starting the machines, you may not get the discharge, but that you will have certain mechanical losses. Okay, so the head curve will have maximum value of head when the discharge is 0. Okay, so the head will be maximum when your discharge is 0. So the output curve will start from origin as that Q is equal to 0. The output also will be equal to 0. So that is the operating characteristics curves. Please see the diagram. you can see that the graph efficiency, power and head are along the y-axis, okay, and you can see that discharge is along the x-axis. The first one, you can see the head, how it is varying. First, you can see that when the discharge is actually, we don't have it as the head is starting, okay, from this head discharge power and head. So it starts from 0 and it goes on decreasing somewhat. You can see the discharge and the head is actually decreasing, okay, and but you can see the relationship with the help of this curve. When you take it as an efficiency, it's actually first it is rising. The efficiency is rising with the increase in the discharge, and after a certain time it's coming down. You can see that curve, okay. Next is actually your input power. So how it is input power? The input power, you can see it's increasing with your discharge, and the curve ratio or the curve slope is you can see how it is. First it is rapid and then gradual, and next one we have it as output power. So what it is actually, the speed is kept constant. You're keeping a speed is constant. Now what happens here? Actually here it's increasing and then again it starts decreasing, okay. And when the discharge is going on increasing also, what happens? This is actually the output power slightly decreases when the speed is kept constant. And next one, constant efficiency. See, for obtaining the constant efficiency curves for the pump, the head versus discharge curves and efficiency versus discharge curves. So for various speed it has to be used, okay. This head versus discharge curves for different speeds also you have to be drawn. The efficiency versus discharge curves for different shades, it has been shown in the diagram. So by combining all these diagrams or graph what we have done before this figure, we will have to get the constant efficiency curve as shown in the diagram. You can see this. So this is actually the first, you can see the head, okay. This actually the first line, it shows that H and Vs and Q is actually a you are keeping this H, Vs and Q. So how they are varying when this head is along the y-axis, and for various speeds how we are getting your head, okay, how we are getting your head. And you can see that the constant efficiency curve, how it is when how you can see that is actually, you can see that this curve is you can see it as 8 so 8 how it is actually plotting. We are taking the certain points for various speeds and you are getting this curve, isn't it? And from these we are pointing out and we are getting your constant efficiency curve. When you take it as your constant efficiency curve, this efficient curve is efficiency is along the y-axis and discharge is along your x-axis. So what happens here? A, B, C, D. This is for various speeds: N1, N2, N3, N4. Okay. So you can see this. How is this N1? Okay. So N1 actually you can see this is a constant. You can see a line which is your constant efficiency line. Okay. So this will be your. You can get it as your, this is actually your, what it is called as constant efficiency curves are obtaining like this model. And actually what is the next topic is cavitation. So what is actually cavitation? So cavitation is defined as the phenomenon of formation of vapor bubbles of a flowing fluid in a region where the pressure of the liquid is below the vapor pressure. We will have some bubbles, okay, and this sudden collapsing of these bubbles will happen when it of higher pressure. Actually the formation of bubbles will takes place in low pressure, and these bulbs will they will be collapsing at high pressures, okay. So when they are collapsing, what will happen? High pressure will be created and the metallic surfaces above this vapor bubbles will collapse subject to high pressures, so causing pitting action. So these cavities will be formed on the metallic surface and also considerable noise and vibrations are being produced. So how to handle how to overcome this cavitation? So pressure of the flowing fluid in any part of the hydraulic system should not be allowed to fall below the vapor pressure, okay. So if it is falling below the vapor pressure only, you are getting a this bubbles. If the flowing fluid is water, then the absolute head should not be lower than 2.5 meters of water, and we should have special materials or coatings such as aluminium, bronze and stainless steel. So they are cavitation resistant materials, okay. So thanks for your listening, okay. So we shall be meeting in the next section. Thank you all once again.